Okay, gang, here we go. So this is Chem 2 Unit 3. We're talking about stoichiometry today. So this should be pretty fun. Pretty short video. We'll talk about it a little bit and then do a couple practice problems here. Okay, so essentially, this kind of brings to focus why we spent all that time balancing chemical equations. So in this example here, we've got 2H2O, or 2H2 reacting with O2, making 2H2O. All right. So these coefficients can really be interpreted two different ways. One way we can think of these as like two molecules of H2 reacting with one molecule of O2 and forming two molecules of H2O. So that's one way you could think of it. And we also know because the change between molecules or formula units and moles is just Avogadro's number, the 6.02 times 10 to the 23rd, right? We can just run with this idea and then we can say, oh, well, if we have two molecules, that's the same thing as saying 2 moles of H2 reacting with 1 mole of O2 forms 2 moles of H2O. And that's really what we're going to use those values for, is these ideas that it shows these mole ratios. Then if if you want to convert them to mass, because really this is the most handy because we have balances that can tell us the mass of the things that we're working with. So we can use, if we want to convert it to mass, we have to use these molar masses. Okay, so that's the whole reason we have these balanced chemical equations, is so that we can figure out how many moles, molecules, and grams we have of whatever it is we're working with. Okay, so this is like the general outline of how one of these problems work. Okay, so you start with grams of substance, right? We'll call it A, and this gives us the molar mass of A, and then we can, using the molar mass of A, we can convert it to moles of A, and then use the coefficients. This is also called the mole ratio, right? We can use the mole ratio to convert it to moles of substance B, and use the molar mass of substance B to convert it to grams of substance B. All right, so that we use that mole ratio in order to go from moles to moles. All right, so let's do our roadmap here. So we did this, we started this a while ago. All right, so we've got moles of A, and we've talked about so far how to convert from moles of A to mass of A, right? And in order to do that, we use the molar mass, and it has the units of grams per mole, right? Grams per mole. And then we also have, for moles of A, we also have formula units. Remember our formula units? And so this, it uses Avogadro's number. Avogadro's number. Okay, 6.02 times 10 to the 23rd. And then now we have this new tool that allows us to go from moles of one thing to moles of another thing. So now, instead of being A, I should add this A, formula units of A, we go to moles of B. All right. And in order to use that, we're going to use this mole ratio. Okay. And this comes from the balanced chemical equation. So we'll maybe get a little note here, balanced chemical equation. All right. Balanced chemical equation. And then once we're at moles of B, then it's a simple matter of just going, we can just use the molar mass of B to convert it to mass of B. So we'll just molar mass, we'll just notate that it's for B. This guy was for A. I'm adding stuff after the fact here. And then we can go from moles of B to formula units of B, right, using Avogadro's number. And Avogadro's number is the same for everything, right? So anyway, so that's our roadmap. And so if you have a hard time thinking about this, maybe think about putting this on a note card that you can carry around with you while you do your practice problems and study for the quizzes and exams. All right, so here's a practice problem, and they're asking us, it's like, all right, we're starting with 1 gram of glucose. We want to know how many grams of water can we make. How many grams of water can be produced from 1 gram of glucose? All right, so we're starting with 1 gram of this, and we want to figure out how many grams of that we can make. So we always start with what we're starting with. So we've got 1 gram of glucose right here. And in order to do this, remember we're starting with grams of glucose, A, mass of A, and we have to get to mass of B, which in this case is our water. So the first step is we have to go from mass of A to moles of A. And we have to go from moles of A to moles of B, and then moles of B to mass B. So this is 3 steps, right? 1, 2, and then 3. Back up again. All right? So the first step is to go to moles of glucose. Well, we figured out in previous video that the molar mass of glucose is 180 grams per mole. So we can divide by that. So the grams of glucose go on here, and then they go on the bottom, and then we have moles of glucose up top. All right. Then we're going to go to moles of substance B, and this is where we're going to use that mole ratio. Okay. So we put moles of glucose in the bottom, moles of water up top, and we have this balanced chemical equation. Notice that the water has a 6 in front of it. That's the coefficient. And then the glucose, that has to be a 1 because there's nothing written there. So then there you go. We put the 6 with the water and the 1 with the glucose. All right, so now we're in moles of water, right? The grams of glucose cancel with the grams of glucose here. The moles of glucose cancel with the moles of glucose, and the moles of glucose cancel here, so we get moles of water. Final step is to get grams of water, so all we have to do is use the molar mass of water and multiply. Now, it says here you can do each step separately, or you can do them in one calculation. So I would always do these in one calculation because it reduces chances of rounding error. All right. So anyway, so if you started with 1 gram of glucose and reacted them in a perfect reaction just like this, essentially we're just burning it, right? This is a combustion reaction. And then, so if we burn 1 gram of glucose, we should end up with 0.6 grams of water at the end. All right. Just like a little side note here, just keep this in mind that heat, although it doesn't appear in a balanced chemical equation, it is related to the balanced chemical equation. Okay, so keep this in mind in the back of your head. Here in chapter 5, we'll get to this point where we're talking about thermochemistry. All right, so let's do a practice problem here, and then we'll call it a day. Okay, so we've got sodium hydroxide reacting with carbon dioxide, forming sodium carbonate and water. Okay, and we want to know how many grams of sodium carbonate can be prepared from 2.40 grams of sodium hydroxide. All right, so we're starting with 2.40 grams of sodium hydroxide. So we'll write that down first, 2.40 grams of NaOH. All right, so we want to get to grams of sodium carbonate. Well, this is essentially just the same problem we solved. So we have to go from grams of this to moles of sodium hydroxide to moles of sodium carbonate and then to grams of sodium carbonate. All right, so here we go. All right, so we draw our parentheses. Put grams of NaOH in the bottom because that's what we need to cancel. We'll put moles of NaOH up top because that's what we need to cancel, or that's what we need to go to. Here, let's erase this guy. I don't like how this is looking right now. See if we can't clean this up a little bit. All right, let's see. So we've got 2.40 grams of NaOH. All right, and we need to get to moles of sodium hydroxide. All right, so we'll put grams of sodium hydroxide here. We're going to put moles of sodium hydroxide here. All right, now we need the molar mass of sodium hydroxide. So sodium hydroxide has one sodium, one oxygen, and one hydrogen. All right, and we got to add those guys up. So sodium, now according to my periodic table I'm looking at here, it's 22.99. All right, so 22.99. And then we have one oxygen, which is 16.00, and then hydrogen, which is 1.01. And we add all those guys up. So we say 22.99 plus 16 plus 1.01. We get 40. All right, so the molar mass, 40.00 grams per mole. All right, so we put a 1 with sodium hydroxide, and we put 40.00 grams in the bottom. So now we're in moles of sodium hydroxide. So now we got to go to moles of sodium carbonate. So we'll put moles of NaOH in the bottom, okay, and then moles of Na2CO3 in the top. All right, we use our balanced chemical equation. Really, we should have, the very first thing is we should have checked to make sure it was balanced, but I kind of just assumed it was balanced because I had the coefficient out front here. So 2 sodiums, 2 sodiums, 2 oxygens, 4 oxygens, 1, 2, 3, 4 oxygens, 1, 2 hydrogens, 2 hydrogens, and 1 carbon, 1 carbon. So we're good. All right, so the coefficient in front of sodium hydroxide is that 2, so we'll put a 2 down here. All right, and the coefficient in front of sodium carbonate is 1, so we'll put a 1 right here. All right, so that's that. Okay, now we're in moles of sodium carbonate. All right. So last step, right? 3-step problem. So we're going to put moles of Na2CO3 in the bottom. Put grams of Na2CO3 in the top. 1 moles. All right, so now we got to figure out the molar mass of sodium carbonate. So we have 2 sodiums, we have 1 carbon, and we have 3 oxygens. This number is going to be bigger. So we have 2 times 22.99. Okay, that's the molar mass of sodium, and there's 2 of them. And then we have 1 carbon, so that's the 12.01. And we have 3 oxygens, so 3 times 16.00. All right. So we take 2 times 22.99 plus 12.01 plus 3 times 16. You get 105.99. Let's just double check, make sure I didn't foul it up. 2 times 200, 3 times 60. Yeah, 105.99. 105.99 grams per mole. So we'll put 105.99 up here. All right, so now we're in grams per sodium hydroxide, which is exactly what we wanted to find. So now we just plug it on into our calculator. Now remember, do it all in one step to reduce rounding errors. All right, so we take 2.40 divided by 40 divided by 2 times 105.99. And I got 3.1797, and we need 3 sig figs, so it becomes 3.18 grams. 3.18 grams. And it would be Na2CO3. 3. Yep, which is A right there. And that's it. That's figuring out stoichiometry. So they get more complicated. We're going to do some limiting reactant problems, percent yield here in a second. But other than that, that's pretty much straightforwardness of sodium or stoichiometry. Let me know if you have any questions.